today we will discuss further about a PID temperature controller, because in the last class we had explained what is PID controller, how to design P stage, I stage and reference stage, and then also I said how to set these time constants. Now we re-look at this PID temperature controller, and then we look into the other issues now. Actually, if you look at the controller, PID controller in general, for example, you have three stages. That is, one is input stage design, that is sensor plus other associated circuit, sensor plus other circuits like temperature compensation, ambient temperature compensation and so on is one area. Then from here we have to go to the PID stage. Then we have the third area, that is a heater drive. These are the three distinct areas are there, and which has to be looked into that separately. So as far as this sensor is concerned, we had seen two different sensors actually, one with the IC sensor and another with the thermocouple. The two examples we had seen how to design the this sensor circuit. PID control, we had shown how to design P separately, I separately and differentiator separately. Heater drive we have not seen extensively, so heater drive also we had to see what are the different possibilities are there, and then also we had said that how to set proportional time, proportional gain and inductor time constant, differential time constant and so on. What is the actual electronic time constants, and then physical time constant, how they differ, that also we have to see in detail. Now first let us take this sensor circuit, design circuit. Now for example, we had to look into different types of sensors, like for example we can take now other important sensor, that is our platinum resistance, platinum resistance thermometer, platinum resistance thermometer. Suppose if I use PRT as a sensor, then how to design that stage, because in analog circuit design handling the sensor is a very important thing, and then how to compute the error budgeting for that is an important thing. We are not discussed the error budgeting and so on for quite long. We are moved into PID temperature controller, because our main aim is not the PID temperature controller. Our main aim is how to design analog circuit. That is the issue in this course. So on the way we will look into PID temperature controller, but not our focus is the control. Our focus not the control, but actually the sensor design and the circuit design. So let us look into the input stage, that is now we will take platinum resistance thermometer and see how to design a sensor circuit, how to make a PID using platinum resistance thermometer. And our platinum resistance thermometer, for example, if we look at the commercially available sensors, you have say 100 ohm thermometer resistance element, platinum resistance element is available as a sensor. Now if you look at this with the temperature, this resistance goes up by 0.4% actually. That means every 1 degree rise in temperature will increase the resistance by 0.4 ohm, because this 100 ohm is the basic element at 25 degrees C. So every 1 degree will increase the resistance by 0.4 ohm. So suppose if I want to use this and make a temperature controller, how to go about doing this? Now simplest way of doing this would be passing a constant current source to this, that is, I have a constant current source. So obtained from plus 15 volt. Say for example, if I have a 1 milliampere current, it gives you constant current always, assume it is 1 milliampere. Then when it is 100 ohms, say at 25 degree it is 100 ohms, so you will get 100 ohm into 1 milliampere, that will be 100 millivolt. And when that is you will get at 25 degree C 100 millivolt. when temperature goes to 26 degrees C, we will get the resistance becomes 100.4 ohms, and then the resistance, the voltage becomes 100.4 into 1 milliamps, that will be 100.4 millivolt. That means the sensitivity becomes 0.4 millivolt per degree C. So sensitivity, if I use this system, then sensitivity is equal to 0.4 millivolt per degree C. That means per every 1 degree change in temperature, we will get 0.4 millivolt change at this point. This is actually quite enough, because if we see our earlier thermocouple, it was only 40 microvolt per degree C sensitivity, whereas this is 0.4 millivolt per degree C we are getting, and our other sensor, that is namely IC sensor, was giving us 10 millivolt per degree C, which was very high. Of course, we can increase this by increasing this current, but once you increase this current, the self heating becomes more, and that creates problem. Of course, we can go, for example, say 5 milliampere current source if I make, then this will be 500 millivolt, that is at 25 degrees it will be 500 millivolt. At 26 degree it will become 100.4 into 5 milliamps, that will become 502.0 millivolt, because if I multiply this, then the sensitivity actually becomes not 0.4, it becomes 2 millivolt per degree C. So by increasing the current, we can get more sensitivity. Now it is a compromise between the self heating, because if I put more current, then the more self heating takes place. So more self heating takes place, then the accuracy lost. But if I give less current, then sensitivity reduces. So you can increase the sensitivity by increasing the current, but at the cost of self heating, which gives a temperature error. So in this case, let us take, for example, 5 milliampere current and then produce 2 millivolt per degree C sensitivity. So the question is now how to design this constant current source, because constant current source is an important element in analog circuit design, and that is to be the constant current source will be extensively used. So one should know how to design a constant current source. So let us see how to make this constant current source. Now what I do is that we have different types of constant current source. I will just show you the two different types at this point. So I can make, for example, this is one constant current source which is popularly used. So you have plus 15 volt, and then this is load. Of course, supply as plus 15 minus 15. Well, this is a simple constant current source where through this load, if you see this current through this load is always constant, in the sense that whatever may be the resistance value of this, current flowing through this will be constant. This current actually is given by, if I take this as Vz and if this is R, is actually Vz by R. So that is the current that is always flowing irrespective of this load resistance. So current is constant even if I change this resistance. This is that's why we call this a constant current source. In our case, what we are going to do is we are going to connect our thermometer, that is our platinizer thermometer, in this place of load. So essentially it looks like this. If I look at our temperature sensor, that it looks like this. So here the temperature sensor is put, PRT is put here, which is acting as a load now. then why the current through this is constant, I is constant, why it is constant. Now to understand this we look at the circuit here. Now for example this is Vz, suppose if I put 5 volt Zener, that means voltage across this is 5 volt. We already discussed about this. For example, I can use a Zener diode like lm336, available in 2.5 volt as well as 5 volt configuration. I take 5 volt lm336. So if the current is 1 milliampere through this, then if the current is 1 milliampere through this, then we know there will be a 5 volt across this. So how to maintain 1 milliampere through this, because the 15 volt is applied now between this and this resistance. So if the voltage is 5 volt across this, the remaining 10 volt will be across this, because total voltage is 15. So the current through this and current through this are same. That means if I want 1 milliampere through this, I also maintain 1 milliampere. But the Zener specified as 1 milliampere minimum current, the maximum current can go up to 10 milliampere. So let us work out, take as 2 milliampere current, I maintain 2 milliampere, so I maintain here also 2 milliampere. So if it is 10 volt across this, 2 milliampere if I need, I have to put 5k, so I put the nearest value of 4.7k here, which will make sure a little more than 2 milliampere current that is flowing through this. So that will make sure the voltage across this is 5 volt. If the voltage across is 5 volt, then if this is 15, then automatically this comes to 10 volt. So plus is 10 volt. Then if it is plus is 10 volt, then what will be the voltage at this point? We know that voltage at this point will be equal to this when in a closed loop system in the op amps, because this and this must follow each other. So I will explain more about this. Now we will see, if I assume this is also 10 volt, then if this is sitting at 10 volt all the time, because this is sitting all the time 10, so this will be sitting all the time 10, then automatically it becomes voltage across this becomes 5 volt. That means if I take this is 10 and this is 10, then voltage across the Zener is equal to voltage across this resistance R. So that comes automatically. Even if this voltage goes up, then this also will go up, and this also will follow that, and automatically voltage across this will be equal to this. So essentially voltage across R becomes this. And if I assume that whatever current is flowing, the actual everything is going through this, and assuming the base current is negligible and assuming this current negligible, then the current flowing through R is actually the current flowing through this load. That means the current flowing through this R is same as current flowing through the load. Since voltage across this is constant, which is equal to Zener diode, so current through this is constant, automatically current through this also constant. So we can say voltage across R is equal to Vz. So current I through the resistance R is equal to Vz by R, because voltage across this is known, so R is known, so current through this is this. So that's why the current through this is constant, and that is given by this amount Vz by R. So that's how the current is constant. So even if I vary this, current will remain constant. But actually how the circuit is working, leaving this mathematics, if we look at how the circuit working, we can approach this in a different way. Assume that if this is 10 and if this is not 10, suppose if this is more than 10, say 11 volt, suppose if it goes more than 10, say 11, then this point will come down, because this is 10 and if inverting input is 11, so automatically this output will go to minus 15, and if this is sitting at plus 11, the enormous base emitter voltage difference comes, then automatically it conducts heavily. If it conducts heavily, more voltage drop will occur and this voltage will come down. That means once it goes more than 10, say it goes 11, then the conduction increases and that pulls down this voltage. Other way around, suppose if the voltage is not 10 and if this voltage is say 9, then if this is 9 and if this is 10, then output will go to plus 15. If this is the base is plus 15 and if this is sitting at 9, that is what we will assume, then this is reverse biased, no current will flow. If no current is flowing, then no voltage drop across this. So if this is 15, then automatically if there is no current, then there is no voltage drop and this also becomes 15. That means if I assume this is lower, then automatically current reduces and makes this point go high. So other way around, this if it is 10, this has to stay only at 10. If it goes more, then automatically it pulls down, and if it comes less, automatically the current reduces and this point goes up. So eventually what happens that this voltage 10 and this also comes to 10. That is how it regulates and keeps the current constant. Of course, our assumption is valid only if this current is negligible and the base current is negligible. Anyway, the base bias current of the op amp is small, that is negligible. So if you want to make this current, the base current small, we can use a Darlington. For example, I can always put a Darlington here and redraw the circuit. So I can put a Darlington here. So obviously now whatever current that is coming here, only beta times, that is 1 by 100th of this current only coming here, and that current also most of them running here, only 1/100th of that only flowing through this. For example, if I want 5 milliampere current through this, if I take this what is required is 5 milliampere, then obviously if this current is 5, then this will be 5 by 100. If the HFE is 100, 5 by 100 will be 50 microampere. Then this base current will be 50 microampere divided by 100, that will be 0.5 microampere only will be flowing from here. So this current will be 0.5 microampere. So the base, obviously this current is negligible. So if 5 milliampere comes, all the 5 milliampere goes through this, only 0.5 microampere is going through that can be neglected. So by this way the current is maintained constant. Of course, current will change only if this resistance drifts. For example, if the resistance changes with temperature, then the current will change. Then if the Zener voltage changes with temperature, current will change. If the offset voltage of this op amp changes, then the current will change. Otherwise the current will remain constant. So of course these errors we have to look into. If the transistor base emitter voltage changes, the current will not change, because the base emitter voltage is in the closed loop. For example, all that matters is if this is at 10 and this will be less by 0.6, that means this point will be 9.4 and automatically this will be another 0.6 less, that will be 8.8. But when temperature, assume that temperature goes up, instead of 0.6, if it becomes 0.5, this is 10, this becomes 9.5, this becomes 9, that is all. So the base voltage, the output of the op amp have to change when temperature changes, but then the output have to change say by 0.1 volt, the required difference change is 0.1 divided by the open loop gain. The open loop gain is very high. So if the base emitter voltage changes with temperature, then output voltage have to change by say 0.1 volt or 0.2 volt, then required change here, because this is remaining 10, the required change will be only few microvolt, because the gain is very large. At any given time, the difference between the two inputs multiplied by the open loop gain is the output. If the output change has to be if it is 0.1 volt, then change required will be in few microvolt, then change will be here few microvolt. The current change because of that will be negligible. Of course, there will be a current change that is negligible, that is all, because it is reduced by the open loop gain times of the op amp. So if the temperature changes, the transistor base and voltage changes, it will not give any error in the current, but offset voltage change will give error, Zener drift will give error, and the resistance change will give a current error. So this way the you can design a constant current source to energize the our PRT which was used, which is used as a sensor. Of course, if I want, for example, in this case, our example, we wanted 5 milliampere current, then our Zener is 5 volt, so that will be 5 volt, and to get 5 milliampere, I had to have 1K resistance. which will give me 5 milliampere current, constant current source. So in actual case the PRT is actually connected like this. So what we do is we will have this constant current source. Of course now I can draw both of them as a Darlington pairs. This is our I put it as a our load like this now, then connect this goes 2 plus 15, and then here actually we will have our Zener connected, and this we already decided 4.7 K. For example, we can use transistor like 2905 is a good choice, which has 100 volt collector emitter breakdown voltage VC of 100 volt breakdown. So which we are using only 15 volts. So this kind of transistor is perfectly alright, and this is our PRT. Now the PRT normally has to be put inside a oven or somewhere where the temperature to be maintained, because we want to measure the temperature of the oven and maintain that at constant. So the PRT may have a long wire. So in practical terms this looks like this, the PRT connection looks like this. So we have a long wire and goes there and comes back. So this is the length of the wire that is used to carry this one, but normally you will put a copper wire here and copper wire here. So when room temperature changes, this will be kept inside the oven. This is PRT. This is kept inside the oven, so that temperature it measures. But then this connecting leads, which are actually this one and this one, if it is longer, then they also add a resistance. So if I try to measure the voltage here and here, between this point and this point, then I am measuring the platinum resistance thermometer's resistance plus the wire resistance, the copper wire resistance. The problem with this copper wire is the copper wire also changes the temperature. Maybe this is in room temperature. Now the problem is, but room temperature also, if the wire resistance is appreciable, then you will have a this resistance also will change with temperature, and then we will get a wrong reading here, because we want to measure only the change here, not the change in the resistance, because the resistance wire resistance also will change when it is appreciable. So to want to make measurements, then what you do is we will make the two more wires we take from here, one wire from here, one wire from here, and we will take the voltage across this. We measure with the high impedance amplifier this voltage, so that there is no current through these leads which are carrying the voltage. So actually this is a 4-terminal method, because you have 1 wire, 2 wire, 3 wire, 4 wire. These 2 wires are carrying the current, this wire and this wire carrying the current, whereas these 2 wires are carrying the voltage. And of course we have to measure it with high impedance, so that high impedance amplifier, so that there is no current flowing through this, to make the measurement accurate. So this is normally done, this 4-probe method is used normally when you are looking for a high measurement. So if you want this, then I can amplify this voltage using an amplifier. Now for example I can use different amplifiers. This I can put a for example, only simplest thing is I can use a difference amplifier. So that only the difference between these two voltage amplifier. Of course I can keep this resistance higher, this resistance is higher, say I can put 100K 100K, so that I have only gain 1, because now it's a difference amplifier of unity gain. So the difference between these two, the difference between these two is now appearing as it is here. And since this is 100K, the current flowing through these leads are very small. and because of that there is the negligible voltage drop on this wire. So, exact voltage between this point and this point is now reproduced here. The difference between the whatever voltage difference here, that is reproduced as it is here without involving these connecting lead wire resistances. So, that makes our measurement accurate. Now, this can be used further for controlling, because this if you want to use it for control, then I have to find the error voltage. So, I take this and subtract with respect to reference temperature, then I can get a difference, and then I can do the same thing which I had done earlier, that is in the case of thermocouple we had done the same thing can be done. I will not repeat this, but I am just concentrating on this sensor design. So, now having done this sensor design, let us look into how to make error budget for this, because we have not done this for quite long. Of course, there are various options. We can have a instrumentation amplifier here rather than a difference amplifier, which will give a better result. We will talk about that more. Let us see the total errors involved in this. Now, if you look at this, our Zener, okay, we will redraw the circuit for error budget purpose. So, if I redraw the circuit and then try to find the error budgeting, so I will concentrate now only on the resistance simple circuit. I take constant current source and then simple load I take. Find out what is the current error here with current drift. I drift is how much? I drift is how much? That is our main aim. So, you take this plus 15 and then this is 4.7 K. This is LM 336 Zener 5 volt. This is R, which is actually 1 K resistance. Assume that I had used say 741 here. General purpose op amp, which comes to our mind immediately. So, let us assume I use 741. Then let us see, if I had used 100 ohm flat resistance thermometer of 5 milliampere current, what is the drift that you can expect in I this current, and then because of that what is the expected temperature error, we try to find out in this case. So, first to take Zener drift, this minus 15 is given here. So, let us take the Zener drift. So, if this is Zener is having 30 ppm per degree C drift. So, for 100 degree temperature change, because if I am designing for industrial grade, then 100 degree temperature change should be considered. So, for 100 degree C ambient temperature change, ambient temperature change, Zener drift, VZ drift, so that is change in Zener voltage with temperature, VZ drift will be 5 volt into 30 ppm, 30 divided by 10 power 6 into 100 degree. So, that is the expected drift in voltage in Zener. That will be equal to 15 divided by 10 power 3, because you have 5 into 3 15 and 10 power 3 goes 10 power 3 here, that is 15 millivolt change. So, with if it is a 30 ppm Zener, then you can expect a 15 millivolt change in the Zener voltage. 15 millivolt change will produce a 15 millivolt change here, that will demand automatically 15 millivolt change here. That means 15 millivolt change you have to occur across this resistance, that what will be the current change. So, the current error, so current drift, drift due to VZ drift. Current drift, so that will be equal to current drift due to VZ drift would be that 15 millivolt is the actual change in the Zener voltage divided by 1K, that will be 15 microampere. So, there will be a 15 microampere current drift due to the change in Zener drift. So, current drift due to Vz drift, that is equal to 15 microampere. So, 15 what will be the temperature error that will give 15 microampere current changes through the 100 ohm PRT, then voltage change, that voltage across the PRT will change because the current through the PRT changing with 15 microampere. So, voltage change across PRT due to 15 microampere current drift. That will be 15 microampere into 100 ohms, that comes microvolt, that is 1.5 millivolt. So, voltage across the platinum resistance thermometer will change by 1.5 millivolt, but we know 2 millivolt is considered as a 1 degree C. If 2 millivolt changes across the platinum thermometer, temperature error is 1 degree. So, sensitivity is actually 2 millivolt per degree C. Sensitivity of PRT in this case is equal to 2 millivolt per degree C. So, 1.5 millivolt will give, so error. So, we had find the error due to 1 point error in temperature due to 1.5 millivolt drift, that will be 1.5 by 2 degree 2, that will be equal to 0.75 degree C error. That means because of the Zener drift, you will have a temperature of 0.75 degree in temperature measurement actually. So, this is whether the error is significant or not depends upon the actual application, but you have this much of error is expected. Then we see other errors. The other error will be resistance drift. So, we have this resistance. For example, we take this resistance we call this is R resistance. R drift will have error. Of course, this resistance drift has no implication, this has no problem, because this resistance changes only the Zener current changes, but we know that Zener current changes, the voltage across the Zener hardly changes, so there is no issue with that. So, one need not worry about the this resistance. So, we consider what is the expected current change due to this resistance change. Now, for example, we can have different options for this resistance. Now, assume that if I put this resistance, just for illustrate what happens if I use normal carbon composition resistance of 300 ppm. So, we had find out now temperature error due to R change. We have to calculate this. For this we take resistance value we know is 1K, so 1000 ohms. Temperature coefficient of this for example, we take 300 ppm resistance per degree C, that we know is plus or minus 300 ppm. So, if I take R as 1000 ohms, then temperature coefficient as plus or minus 300 ppm, then our delta T is usually take 100 degree C. There is temperature, expected ambient temperature changes 100 degree C, because this is required for industrial grade equipment. Then delta R, that is change in resistance, when we calculate it like this. So, you have original 1000 ohms into 300 ppm, 300 divided by 10 power 6 into temperature 100 degree C. So, that comes 357. So, 3 into 10 power 7 divided by 10 power 6, that is 30 ohm change. The resistance value will change by 30 ohms. If the resistance changes 30 ohms, that is delta R is 30 ohms, then what is the current change? So because we know the delta I, that is current change, actually is equal to Vz by R. Vz by R is the current through that. So originally we had 5 volt and then we have 1K. 1K, now it becomes 1K plus 30. So originally it was 5 milliohms, 5 milliampere, 5K divided by 1000. Now actually the resistance value, assuming that it had increased, if the resistance, it can increase or decrease, does not matter. We take it here increase and we find out how much current decreased. Other way around, if I take minus, then current would have been increased. So it does not matter because we do not know for a given resistance whether it is increasing or decreasing. That is why we have put this temperature coefficient as plus or minus 30 ppm. So we had find out now what is the error. Now the error would be 5 by 1030 actually. That if we take it will be milliamps. So 5 volt divided by, that is in milliamps, that will actually comes 4, that actually works out 4120. So 5000 minus 4120, it comes to be so that actually comes 880 ohms, that actually make 0. So that will go 8 times, that will go 8 times. So 8240 you will get, that actually gives you 660. So again you make this, that will go 6 times. So it become 4.86 milliampere. So 5 milliampere current had actually become 4.86 milliampere at high temperature. Or other way around, I can also say, if I take this as minus, then it can become 0.14 milliampere higher, that is 5.14 milliampere it can be. Does not matter, we can take in both ways. So if the current, because we do not know in which unit which is whether it is increasing or decreasing. Some unit it will be increasing by the current will be decreasing by this amount, some unit it will be decreasing by this amount, some unit it may not be changing at all because the drift is specified like that, resistance drifts that way. So if it is current delta I, then it becomes, I will take delta I. So delta I actually becomes 0.14 milliampere. It is quite a lot of change. Now what is the temperature error it will give? Then if the current is this much changing, then temperature error can be calculated. Temperature error would be temperature error for 0.14 milliampere current change. That is equal to 0.14 into PRT resistance, that is 100 ohms. So that is voltage, so that will be 14 millivolt change. That is temperature error or voltage error. I can write it as a voltage error here. So voltage error for current change in PRT. So that will be equal to this. So that is 14 millivolt, but we know sensitivity is equal to 2 millivolt per degree C. It is equal to 2 millivolt per degree C, because 2 millivolt changes we take it as 1 degree C. So 14 millivolt gives a total temperature error and 14 divided by 2, that is 7 degree C. So with the resistance, our temperature measurement will go wrong by 7 degree C. So resistance drift is very large, it contributes, gives a large amount of error. Of course, we can reduce this by going for a low drift resistance. For example, instead of 300 ppm, if I go for lower resistance with lower drift, then temperature will come. For example, if I take for 25 ppm resistance, then the error will come down appreciably, because 25 ppm and 100 ppm or 300 ppm are actually by a factor of 12 difference is there. So this also error also will come down by 12 times. So that means error will come to roughly 0.5 degree if I use 25 ppm resistance. Why I had shown this calculation is how important is the temperature drift of the resistance. One have to realize, because very often we ignore this fact. But if you ignore this, then you will end up in having very large drift in the parameters. In this case, the temperature measurement is the actual issue. So error in temperature measurement will, in this case, will go very high. That is 7 degree error will come if I use ordinary 300 ppm carbon resistance. But if I go metal film resistance of 25 ppm, automatically the drift will come down significantly. One can calculate and see this. I leave this exercise to you, I will not repeat this. Now there is one more error that we have to calculate, there is offset voltage drift. We have to calculate the offset voltage drift error. So we will see this, what will be the error due to the offset voltage drift. There is offset voltage drift of the operational amplifier. So error due to offset voltage now. In this case, we have taken 741 as a operational amplifier. So V offset drift of 741, if we see V offset drift of 741 is given as plus or minus 15 microvolt per degree C. Delta T, we take it as 100 degree C. So total offset voltage drift, that total offset drift will be 15 into 100, that will be 1.5 millivolt change. So the offset voltage will drift by 1.5 millivolt if I use 741. Now we have to find out what will be the current error. So current error due to V of drift of 741 is will be equal to, because 1.5 millivolt drift in the offset voltage will be equal to 1.5 millivolt drift in the resistance R, because if we take the circuit here, and the circuit is here, that is if we take 1.5 millivolt drift in the offset, means I have to add here plus or minus 1.5 millivolt. That means this also had to drift by 1.5 millivolt. That means voltage across this will change by 1.5 millivolt. So 1.5 millivolt divided by 1K, that will be the current change. So that will be 1.5 microampere current change. So if I write this, so current change due to the offset voltage drift, current error, that will be equal to 1.5 millivolt divided by 1K, that is equal to 1.5 microampere current. So 1.5 microampere current will have a will change through the platinum resistance thermometer. So, voltage across change in voltage across 100 ohm PRT will be equal to 1.5 microampere into resistance value 100 ohms, that will be 150 microvolt. So, 150 microvolt is the expected change in voltage across the PRT due to the offset voltage drift, but then sensitivity is 2 microvolt here. Sensitivity at this point is again it equal to 2 millivolt per degree C. So, 150 microvolt will corresponds to if I convert into millivolt, that is 0.15 divided by 2 degree, that is 15 by 200, that is actually that is the temperature error, that will actually corresponds to 7.5 by 100, that 0.07 degree error. It is negligible actually. So, temperature error is equal to temperature error due to offset voltage drift. Op-amp is 0.075 degree, which is very small. So, one need not go for high cost low drift op-amp. 741 itself is good because the error what will come is less. The reason is that we had used 5 volt Zener reference. So, when you compare to 5 volt, 1.5 millivolt drift in offset is very small, because 5 volt is our reference, and if we compare 5 volt and 1.5 millivolt, that is the ratio is very large. That is why we got a very low drift due to offset voltage drift. So, one can use 741 itself for this temperature measurement. So, this I had shown you how to make this sensor, how to make this temperature sensor for the controller using platinum resistance thermometer. Of course, we have to now see other issues, because there are so many sensors available, LVDT and so on, which we will discuss one by one little later, because my aim is here how to design a temperature controller including sensor design and then the heater drives design, because our aim is, in this course, make you a good circuit designer. You should be able to design any analog circuit for a given application, and this will help you in electronics quite a lot, because if you are not able to draw a circuit, then you will not become an electronic engineer, however good in other aspects in electronics. So, the learning circuit design is essential part of electronic engineers life. That is why I am more concentrating on the sensor circuit design. Now, you may wonder that we had shown here in this example how to design a temperature sensor using platinum resistance thermometer. Earlier I had shown you how to design using thermocouple, and then also I had shown you how to design the temperature indicator using IC sensor. Of course, this sensor design, using this platinum thermometer, we are using constant current source and power probe method. We can also have different constant current sources, because this is one constant current source wherein we are using Zener diode in a different fashion. That is, we had used the Zener diode referred to supply voltage, because Zener diode is kept Zener diode is kept in this case here, the that is Zener is kept between supply and the op-amp. The Zener, in this case disadvantage is the Zener diode is not referred to ground, because normally in instrument you may have a Zener diode already available which is used for some other purpose. The same thing can be used for this purpose, because in the whole circuit the most costliest item is the Zener diode. if because if you want a load temperature drift current, then I use a load drift Zener. We have taken LM33 which is 30 ppm Zener. We have for example LM339 which is 1 ppm temperature coefficient Zener. But then if you go for that it costs more. So normally Zener costs quite a lot. So if you are using for some other purpose in the circuit one Zener, the same Zener can be used here, but then this Zener is not with respect to ground. So it is better to have a constant current source whose Zener reference is with respect to ground. So this the constant current source design can be looked in a different way. For example, I can have a constant current source which is with respect to where the Zener is connected with respect to ground. For example, I can design a current source now using a Zener with respect to ground. Say I can do it like this. I can take this op amp. Then what I do is I will put for example one resistance here. Then I put the Zener. My aim is that I want the Zener with respect to ground. So I put the biasing network for the Zener, then I give the supply for this plus 15 minus 15 volt, then I give here plus 15 volt. The same 4.7k resistance I put, so that 1 milliampere current minimum maintained. Now in this case 2 milliampere current will be flowing because this is 0, voltage at this point is 0, so this comes to 5 and this is 15, so 10 volt across this 4.7k will give you little more than 2 milliampere. So the same arrangement we can have. Now what I do, I will take this, this, say I connect to plus 15 volt, and then I will connect this point. Instead of connecting it there, I connect it to this point. Because if this is, if this is hitting at 5, and this also had to come at 5, that means this is also at 5, that means voltage across this, voltage across this is always 5, that is equal to Vz. So voltage across this is 5 volt, that is equal to Vz. And if I assume that the current that is flowing here is same as this, the current flowing through this is flowing through this same, and the base current is negligible. If I assume that, then the current flowing through this is same as this. If this resistance equal to this resistance, then voltage across this will be equal to voltage across this. So if this is 5 volt, then automatically voltage across this also will be 5 volt. So all that I do is, if I have kept here 1k, then I also keep here 1k. Then voltage across this also will be equal to 5 volt. Of course, this is true only when the base current is negligible. I can make the base current negligible by putting a Darlington here, so that the base current is, because if this 5 milliampere, this current becomes where we had shown that this base current becomes 0.5 microampere, which can be neglected. Now I got the voltage across this is a Zener which is 5 volt. Now I can put my regular current source, that our earlier current source, because our aim was that we want to make the Zener with respect to ground, so that I can use the Zener, this Zener for a different purpose. So now I put the load here, that is PRT. PRT is here. PRT is here. Then this plus is there. This I connect to this. Now the current will be constant here. Suppose if I put here again 1k, now this current will be I. It will be equal to, this is Vz. So voltage across this become Vz, 5 volt, that is equal to Vz. Now we know that the voltage across this is equal to Vz. So this voltage is Vz, 1k, and the voltage across this becomes Vz. So the current through this become Vz by this R. That is similar to what we had discussed earlier. So the current is now determined by this Vz. So even if I change the value of this, the current will remain constant. This way we can make the Zener voltage with respect to ground. Of course, there are various other ways of designing. Even this can be modified to get because we are used here PNP transistor. We can also modify this to get NPN transistor working version. But nevertheless, we see what is the other errors that come in if I use this kind of arrangement. For example, in this case, this offset voltage drift will give a current drift due to this, and that will give a current drift due to this. But the offset voltage drift we saw produces very little current drift. So offset voltage drift because of this additional op amp is not a serious issue. The base emitter voltage change is not a issue at all. That is actually controlled by the loop gain, because we know that if this is 5, this is also 5, and this is also 5. So the voltage across this is 5 volt, and the current through this 5 volt by 1k, that is 5 milliampere, the same 5 milliampere current is going, and that pushes 5 milliampere current through this. So the error due to this base emitter voltage drift is not there. This offset voltage drift produces very little error here and very little error here. Of course, the additional error that had come is that if the temperature coefficient of this, suppose if the temperature changes, then what happened, the resistance value will change, and then that will make sure that the current through this is changing. The current through this changes, this current also will change. And if this resistance is having a plus positive temperature coefficient and this is having a negative temperature coefficient, then what will happen is that you will have this current change will occur. But nevertheless, you know, if the current changes, then voltage across this will change, because if this current changing and the resistance also changing, and you will have a voltage change occur. So this the voltage across this will not be Vset. So for example, if this resistance changes by increases by 30 ohms and this resistance decreases by 30 ohm, then what will be the new Vz? The new Vz will be this current actually will come down by 0.14 milliampere. This current will increase by this voltage will increase by 0.14 milliampere. So nevertheless, this, if this is plus and this is minus, we will have twice the drift in voltage, due to resistance drift. This is the disadvantage of this circuit, and also added to that, this resistance drift also will give error, because we don't know what's the drift of this, what's the drift of this, what's the drift of this. So compared to our earlier circuit, this adds more error. So one has to be very careful when dealing with this, because we want to save one Zener which may have low temperature coefficient, but then we ended up in having resistance which is now producing much larger error than what we had thought of it. So one had to look into this aspect also when you are deciding on the circuit and saving the money. So in this class we had discussed about how to design a temperature sensor, temperature indicator using Platin-Nessen's thermometer, and in the process we have discussed about how the constant current source is working and how to compute the various errors involved in the constant current source. So the rest of the things we continue in the next class. Thank you.